Welcome to today's problem walkthrough. In this session, we'll tackle LeetCode problem number 1048, longest string chain. This fascinating challenge dives into string manipulation and dynamic programming concepts. Let's get started and explore the approaches to solve it. In this problem, you are given an array of words, where each word is made up of lowercase English letters. The goal is to determine the length of the longest possible word chain that can be formed from these words. A word chain is a sequence of words where each word in the sequence is a predecessor of the next word. For instance, the word ABC is a predecessor of ABAC because adding the letter A at the third position in ABC results in ABAC. However, CBA is not a predecessor of CAD because no single insertion of a letter can transform CBA into CAD. With this understanding, your task is to find the longest chain that can be formed from the given array of words and return its length as an integer. Now, what is a word chain? For a word to be a predecessor of another, you should be able to insert exactly one letter at any position in the first word to make it equal to the second word. Additionally, even a single word by itself is considered a valid word chain of length 1. Let's look at an example to make this clearer. Suppose the input array of words is B, BA, BK, BDA, BK. The output for this case would be 4. Why? Because we can form a chain like this, a -BA -BDA -BK. Here, each word is a predecessor of the next word in the chain. For instance, starting with adding B gives us BA. Then, inserting D into BA forms BDA, and finally, inserting C into BDA forms BK. This chain has a total of 4 words, so the length of the longest word chain is 4. Now, consider another example. If the input list of words is XBC, PCXBCF, XB, CXBC, PCXBC, the output is 5. In this case, the longest chain is XB-XBC-CXBC-PCXBC-PCXBCF. Notice again how each word is obtained by inserting exactly one letter in the previous word, and the total length of this chain is 5. Now let's examine a third example. If the input array is ABCD, DBQ, ABC, BCD, the output is 1. In this case, there's no valid chain that can be formed where one word is a predecessor of another. Each word stands alone, meaning the longest chain has a length of 1. Finally, let's look at the constraints of the problem. The number of words in the input list can range from 1 to 1000, and the length of each individual word will be between 1 and 16 characters. All words are made up of lowercase English letters only, so you don't need to worry about uppercase letters or special characters. There are a few additional notes to keep in mind. While the words in the input list are not guaranteed to be unique, duplicate words won't affect the problem since they don't contribute to forming longer chains. Some edge cases to consider include scenarios where the input list has only a single word, or when the words vary in length but no valid chain can be formed. Another edge case is when the input size is very large, approaching the upper limit of the constraints. Your solution should be robust enough to handle these situations efficiently. By keeping all these details in mind, you'll be well prepared to tackle this problem and implement an optimal solution. To solve the longest string chain problem, one possible approach is the brute force method where we attempt to generate all possible chains from the given list of words. The intuition here is straightforward. For each word, we try to find all its potential predecessors by removing one character at a time and checking if the resulting word exists in the list. Once we identify valid predecessors, we can use recursion or backtracking to explore all possible chains originating from that word. At the end of this process, we determine the longest chain by comparing the lengths of all the chains we generated. However, this approach has significant drawbacks. The recursive exploration of all possible chains leads to exponential time complexity, as each word has multiple potential predecessors, and the recursion stack also consumes a significant amount of memory. While conceptually simple, this method becomes computationally infeasible for larger inputs, such as when the number of words in the list approaches 10,000. Thus, it is not a practical solution for this problem. A more efficient way to solve the problem is by using a dynamic programming approach combined with sorting. The key insight here is that sorting the words by their lengths allows us to process shorter words before longer ones, which ensures that any potential predecessor of a word is evaluated before the word itself. This makes it easier to dynamically build the longest chain ending at each word. By using a hash map, we can efficiently store the longest chain length for each word as we process it. The steps are as follows. First, we sort the words by their lengths. Then, we initialize a hash map where each entry tracks the longest chain ending at the corresponding word. For each word, we generate all possible predecessors by removing one character at a time. If a predecessor exists in the hash map, we update the current word's chain length as the maximum of its current value and the predecessor's chain length plus 1. Finally, the longest chain can be found by taking the maximum value across all entries in the hash map. This approach eliminates redundant recomputation by leveraging previously computed results, making it far more efficient. The optimized approach of dynamic programming with sorting has a time complexity of n*m squared, where n is the number of words in the list and m is the average length of the words. This complexity arises from generating all possible substrings for each word and performing hash map lookups. The space complexity is n, as we store the chain lengths for each word in the hash map. Dynamic programming with sorting strikes the right balance between clarity and performance, making it the optimal strategy for solving the longest string chain problem. This method was chosen for its efficiency and ability to handle large inputs effectively. Sorting the words ensures dependencies are resolved in the correct order, allowing us to dynamically update the chain lengths without redundant computations. Compared to brute force, this approach is slightly more complex to implement but offers a significant performance improvement. The trade-offs are clear. While brute force is conceptually simpler, it is practically infeasible for larger inputs. By leveraging sorting and a hash map, we ensure that the solution is both efficient and scalable, even for large datasets. To solve the problem of finding the longest string chain, we need to identify chains of words where each word is a direct predecessor of the next. This means that a word can be transformed into its successor by adding exactly one letter at any position. For instance, ABC is a valid predecessor of ABAC. A straightforward, though inefficient, approach to solve this is to generate all possible chains of words and identify the longest one among them. The first step in this brute force approach involves parsing the input list of words and sorting them by length in ascending order. This sorting is critical because a shorter word can only serve as a predecessor to a longer word, ensuring that we only compare words in a logical sequence. This sets the stage for building and analyzing chains systematically. Once the words are sorted, the next step is to establish the predecessor relationship between words. This is done using a helper function called is_predecessor, word1, word2. The function checks if word1 can be transformed into word2 by adding a single letter at any position. To achieve this, we iterate through all positions in word2, remove one character at a time, and see if the resulting word matches word1. With this relationship defined, we can then generate chains recursively. Starting with each word, we use depth-first search, or DFS, to explore all possible successor words that are connected to the current word. During this process, we track the maximum chain length encountered. The recursion terminates when no successors exist for the current word, at which point we return the length of the chain formed so far. Finally, after examining all words, we compute the result by identifying the longest chain length across all recursive explorations. The detailed steps of this approach include a few key components. First, sorting the words by length ensures that we only compare potential predecessor-successor pairs in a logical order. This sorting step has a complexity of n log n, where n is the number of words. Next, the predecessor check involves comparing words of adjacent lengths. For each longer word, we remove one character at every position and check if the resulting word matches a shorter word. This operation has a complexity of L superscript 2 per pair, where L is the average word length. Once the relationships are established, we use DFS to explore chains. For every word, we recursively calculate the chain length by exploring its successors. To optimize this process, we use memoization to store the longest chain length starting from each word, avoiding redundant computations. The time complexity for this step is n*L. Edge cases to consider include scenarios like an empty input, which should return 0, a single word input where the chain length is 1, or cases where all words are of the same length, making it impossible to form a chain. Several key insights make this approach effective. Sorting the words by length ensures that comparisons are limited to valid predecessor-successor pairs. Memoization plays a crucial role in avoiding redundant calculations, significantly reducing the time complexity of the algorithm. Recursive DFS is a natural fit for modeling the chain building process, as it allows us to systematically explore all possible paths in the word relationship graph. Speaking of data structures, storing all words in a set allows for O(1) lookup during predecessor checks, making these operations extremely efficient. The memoization table, implemented as a dictionary, helps us store the longest chain length for each word, enabling quick retrieval. Although the graph formed by these word relationships is implicit, it can be thought of as a directed acyclic graph, or DAG, where DFS explores paths within this structure. Analyzing the complexity of this approach, the overall time complexity is O(n*L superscript 2). This breaks down into O(n log n) for sorting the words, O(n*L superscript 2) for checking predecessor relationships, and O(n*L) for the DFS traversal with memoization. The space complexity is O(n plus L), accounting for the memoization table and the recursion stack used during DFS. To better understand how the algorithm works, let's consider an example input, a BA, BK. This example will illustrate how the words are processed, how chains are formed, and how the longest chain is identified. For the input, a BA, BK, we begin by sorting the words by length, resulting in the order, a BA, BK. Using DFS, we start with the word a. It has BA as a successor, which in turn has BK as a successor, and finally BK. This forms the chain, a BA, BK, with a length of 4. Next, we start with the word BA. Its successors are BK and then BK, forming the chain, BA, BK, with a length of 3. By exploring all words, the longest chain length is determined to be 4, corresponding to the chain, a BA, BK. This demonstrates how the algorithm systematically identifies the longest possible string chain. Here, we start by defining a class solution with a function longestStr that takes a list of words as input. The first step is to sort the list of words by their lengths, which ensures that we process shorter words before longer ones. This is important because shorter words are potential predecessors of longer words in a valid string chain. Next, we create a dictionary called DP to store the longest chain length ending with each word. We also initialize a variable max_chain to 1, which will keep track of the maximum chain length found so far. Now, we loop through each word in the sorted list. For every word, we start by assuming that its chain length is 1, as every word can at least form a chain by itself. Then, we attempt to generate all possible predecessors of the current word by removing one character at a time. For each such predecessor, we check if it exists in the DP dictionary. If it does, this means we can extend the chain ending with the predecessor to include the current word. We update the chain length for the current word in the DP dictionary by taking the maximum of its current value and the chain length of the predecessor plus 1. Finally, we update the max_chain variable with the maximum value between its current value and the chain length of the current word. After completing the iteration through all the words, the function simply returns the value of max_chain. This represents the longest possible string chain that can be formed from the given list of words. By sorting the words up front and leveraging dynamic programming with the DP dictionary, we ensure that the solution is both efficient and correct. The time complexity is primarily determined by the sorting step and the nested iterations, making this approach well suited for handling typical input sizes in competitive programming scenarios. To solve the longest string chain problem, we start by sorting the given array of words by their length. This ensures that shorter words are processed before longer ones, which is crucial for building valid chains. Next, we initialize a hash map called DP to store the longest chain length that ends with each word. This allows us to keep track of the maximum chain length dynamically as we process each word. We also introduce a variable maxchain to keep track of the overall longest chain length found so far, starting with a value of 1 since the shortest chain has at least one word. For each word in the array, we initially set its chain length in DP to 1, assuming it cannot form a chain with any other word yet. Then, we iterate through each character of the word, trying to remove it to create a potential predecessor. If this predecessor exists in the map, it means we can extend the chain ending with that predecessor by 1. We update the chain length for the current word in DP to reflect this extension, taking the maximum of its current value and the chain length of the predecessor plus 1. After processing all possible predecessors for a word, we update the maxChain variable to ensure it reflects the longest chain length seen so far. This step ensures that maxChain always holds the result we are looking for as we iterate through the words. Finally, once all words have been processed, the function returns maxChain as the result, representing the length of the longest string chain that can be formed. This implementation efficiently builds chains by leveraging dynamic programming and sorting, ensuring that we only process valid predecessors and update chain lengths incrementally. To solve the problem, we start with an example input of words, a, ba, bda, bka. The first step is to sort the words by their lengths, which gives us a, ba, bda, bka. This ordering is important because shorter words must be processed before longer ones to correctly build chains. Next, we initialize two variables, a dictionary dp to track the longest chain ending at each word, and max_chain, which keeps track of the overall longest chain found so far, starting at 1. Now, we process each word. For the word a, we begin by assuming it forms a chain of length 1 by itself, so we set dp a equals 1. Since a has no predecessors, removing any character results in an empty string, there are no updates to make. We then update max_chain to the maximum of its current value and dp, a, which remains 1. At this point, our dp dictionary is a 1. Next, we process the word ba. We start by assuming it forms a chain of length 1, so we set dp ba equals 1. Now, we check all possible predecessors by removing one character at a time. Removing b gives a, which exists in dp. This allows us to extend the chain ending at a, so we update dp ba to be the maximum of its current value in dp, a, plus 1, which gives 2. Removing a results in b, which does not exist in dp, so no update is made. We then update max_chain to the maximum of its current value in dp, ba, which becomes 2. The dp dictionary is now a 1, ba 2. Moving to the word bda, we start by setting dp bda equals 1. Checking predecessors, removing b gives d, which does not exist in dp. Removing d gives ba, which exists in dp, so we extend the chain ending at ba. This updates dp bda to 3. Removing a gives bd, which does not exist in dp, so no further updates occur. Finally, we update max_chain to 3, and the dp dictionary becomes a 1, ba 2, bda 3. Now, we process the word bka. We start by setting dp bka equals 1. Checking predecessors, removing b gives dca, which does not exist in dp. Removing d gives bka, which also does not exist in dp. Removing c gives bda, which exists in dp. This allows us to extend the chain ending at bda, so we update dp bka to 4. Removing a gives bdc, which does not exist in dp. With no further updates, we adjust max_chain to 4, which is the longest chain we've found so far. The final dp dictionary is a 1, ba 2, bda 3, bka 4. The longest chain length for this example is 4. In the second example, the input words are x, xy, xyz, z. After sorting by length, we get x, z, xy, xyz. As before, we initialize dp as an empty dictionary and set max_chain to 1. Starting with the word x, we assume it forms a chain of length 1, so we set dp x equals 1. Since there are no possible predecessors for x, no updates are needed. We then update max_chain to 1. The dp dictionary becomes x, 1. The next word is z. Similar to x, we start with dp z equals 1, and since it has no predecessors, no updates are made. The max_chain remains 1. The dp dictionary is now x, 1, zip 1. Now for the word xy, we start with dp xy equals 1. Checking predecessors, removing x gives y, which does not exist in dp. Removing y gives x, which does exist in dp. This allows us to extend the chain ending at x, so we update dp xy to 2. We then adjust max_chain to 2, and the dp dictionary becomes x, 1, z 1, xy 2. For the word xyz, we begin with dp xyz equals 1. Checking predecessors, removing x gives yz, which does not exist in dp. Removing y gives xz, which also does not exist in DP. Removing Z gives XY, which exists in DP. This allows us to extend the chain ending at XY, so we update DP, XYZ, to 3. With no further updates, we adjust max_chain to 3. The final DP dictionary is X1, Z1, XY2, XYZ3. The longest chain length for this example is 3. In the third example, the input words are BAC, base. After sorting by length, we get BAC, base. We initialize DP as an empty dictionary and set max_chain to 1. Starting with the word we assume it forms a chain of length 1, so we set DP equals 1. Since there are no possible predecessors for no updates are needed. We then update max_chain to 1. The DP dictionary becomes 1. The next word is We start with DP equals 1. Checking predecessors, removing a gives B, which does not exist in DP. Removing B gives which does exist in DP. This allows us to extend the chain ending at so we update DP to 2. We then adjust max_chain to 2, and the DP dictionary becomes 1, 2. Next, for the word BAC, we begin with DP, BAC equals 1. Checking predecessors, removing B gives AC, which does not exist in DP. Removing A gives BC, which also does not exist in DP. Removing C gives BA, which does not exist in DP. Since no predecessors are valid, DP, BAC, remains 1. The max_chain remains 2, and the DP dictionary is 1, 2, BAC 1. Finally, we process the word base. We start with DP, base equals 1. Checking predecessors, removing B gives ACE, which does not exist in DP. Removing A gives BCE, which also does not exist in DP. Removing C gives BAE, which does not exist in DP. Removing E gives BAC, which exists in DP. This allows us to extend the chain ending at BAC, so we update DP, base, to 2. With no further updates, we adjust max_chain to 2. The final DP dictionary is 1, 2, basic 1, base, 2. The longest chain length for this example is 2. Here, we analyze the time complexity of the solution step by step. First, sorting the n words by length requires n*log n time. Next, for each word, we attempt to generate all possible predecessors by removing one character at a time. If the length of a word is m, this generation process takes m time per word. Checking if a predecessor exists in the DP dictionary, which is implemented as a hash map, is an O1 operation. Since every word is processed once, iterating over all words with an average length of m contributes n*m to the time complexity. When we combine these steps, the sorting operation adds n*log n, and the processing of words adds n*m, resulting in an overall time complexity of n*log n plus n*m. Now, we focus on the dominant term of the time complexity. Since the maximum word length, m, is generally much smaller than the total number of words, n, the n*m term dominates over n*log n in most cases. Hence, the overall time complexity simplifies to n*m. For space complexity, the DP dictionary, which stores the longest chain length for each word, requires n space since there are n words. The sorting process is done in place, so it uses O1 extra space. Additionally, temporary variables used during iteration, such as predecessor and string slicing indices, contribute only O1 space. Combining these factors, the overall space complexity is O(n). Next, let's examine the best, average, and worst-case scenarios. In the best case, all words have the same length, meaning no sorting is required, and predecessor checks are minimal. This results in a time complexity of O(n). In the average case, words have varying lengths, and most words have a small number of predecessors. Here, the complexity is O(n*m). In the worst case, words have large lengths, and every word has multiple predecessors, requiring all operations to be performed. This also leads to a complexity of O(n*m). Compared to a brute force approach, which would involve generating all possible chains and checking their validity, the dynamic programming solution is far more efficient. A brute force method would take O2 to the power of n time due to the exponential growth of subsets, while the dynamic programming approach reduces this significantly to O(n*m) by leveraging sorting and memoization. Finally, let's mathematically prove the big O complexity. Sorting the words by length is O(n*log n), as established by sorting theory. Generating predecessors for each word involves at most m predecessors per word, each checked in O(1) time. For n words, this totals O(n*m). Since O(n*m) dominates O(n*log n), the final time complexity is O(n*m). On the space side, the DP dictionary requires O(n) space to store chain lengths for all n words, and no additional data structures are created. Thus, the space complexity is confirmed as O(n). When working on chain-related problems, there are a few common pitfalls to be aware of. First, not sorting the input properly can lead to major issues. Many chain problems require the input to be sorted, often by word length or lexicographical order, to ensure chains are built correctly. Skipping this step can result in inefficient or invalid solutions. Next, an incorrect base case in recursion is another frequent mistake. If the recursion doesn't terminate properly, say, when no valid predecessors are left, it may lead to infinite loops or incorrect outputs. Always verify your base case logic. Additionally, overlooking edge cases can be a problem. For example, you might encounter a single word chain, words that don't fit into any chain, or even empty input. These scenarios need explicit handling to avoid runtime errors. Lastly, inefficiency in checking if one word is a predecessor of another can be a bottleneck. Using optimized techniques like character removal or hash-based approaches can significantly reduce unnecessary computations here. Another common issue arises when you ignore overlapping subproblems. Chain-related problems often involve repetitive calculations, and relying on brute force without memoization or dynamic programming can lead to time-limit-exceeded errors, especially for larger inputs. This is where dynamic programming shines. Now, from an interview perspective, recognizing patterns is essential. Many of these problems follow a state transition pattern where you incrementally build solutions. Practicing this helps you identify optimal approaches more quickly. Additionally, dynamic programming is a frequent theme in interviews. Interviewers often expect you to take a brute force solution and optimize it using memoization. Be ready to explain how this reduces redundant work. They might also ask about the trade-offs between recursion and iteration. While recursion is intuitive, it's prone to stack overflow on large inputs, whereas iterative DP is more space efficient. And remember, clear communication is key. When explaining your solution, walk through how you validate predecessors and build chains step by step to demonstrate a solid understanding. To deepen your understanding, it helps to explore related problems. For example, LeetCode 1048, longest string chain, focuses on building the longest chain of words by adding one character at a time. LeetCode 300, longest increasing subsequence, is another classic dynamic programming problem with a similar state-building process. Then there's LeetCode 139, word break. This problem involves segmenting a string into valid words, and it highlights the importance of dynamic programming in solving such challenges. Lastly, LeetCode 472, concatenated words, requires forming words using other words. This is a more advanced variation that often involves tree-based or dynamic programming techniques. By practicing these problems, you'll gain a stronger grasp of the patterns and approaches that can be applied to chain-related challenges. Finally, let's discuss alternative approaches and their trade-offs. Starting with brute force and recursion, this approach is straightforward and easy to implement, making it a good starting point to verify correctness. However, it becomes computationally expensive as the input size grows due to the exponential number of chains to explore. Dynamic programming offers a significant improvement here by storing intermediate results and avoiding redundant calculations. The trade-off is that it requires careful design of the state and transitions, which can be challenging. Another alternative is using topological sorting for directed acyclic graphs, or DAGs. If the problem can be represented this way, topological sorting can efficiently build chains, although it's a less intuitive method. Lastly, a tree-based solution is particularly useful in word-based problems, as it enables efficient prefix or predecessor checks. The downside is its high space complexity, which may not be feasible for very large inputs. Understanding these approaches and their trade-offs will help you choose the right strategy for different variations of chain problems. Great job following along. Today, we explored the longest string chain problem, breaking it down into manageable steps and utilizing dynamic programming with hash maps for an efficient solution. Remember the importance of pre-processing and leveraging constraints to optimize your approach. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!